Okay, so I think we're in a good spot. So hello, everyone. It is my pleasure to introduce Humza. Humza is a machine learning research engineer here at Snorkel, and he works on bringing the latest in ML research into the Snorkel platform. So please join me in welcoming Humza.
All right, cool. Thanks, everyone. Yeah, so I guess without any further ado, let's get started with this paper. And if you have any questions, feel free to just ask if you're confused. But just a fair warning, though, it may be hard for me to read the chat. So I don't know, maybe if Roberto or someone, if you see any questions in the chat that maybe aren't being propagated, if you could just ask me or someone, that would be good. So with all that being said, let's get started. So today's paper that I'm going to be presenting a paper called Epoxy. It's basically using semi-supervised learning embeddings for weak supervision, and I'll explain what all that means soon. So this is the formal title of the paper. It's actually called Train and You'll Miss It: Interactive Model Iteration with Weak Supervision and Pre-trained Embeddings, but the algorithm that they use in that paper that they invented is called Epoxy. So I'll just sometimes refer to it as the Epoxy paper or Epoxy for some ease. But yeah, if you want to look up the full title, then this is it. And many of the co-authors on this paper are fellow snorkelers. We've got Fred and Ravi, and one of the interns on the research team, Faye. She was also here, and of course, Chris Ray, co-founder. So all that good stuff. But yeah, so basically, just some background. So one of the things that we've been we push for really aggressively at Snorkel is the idea of weak supervision. And essentially weak supervision enables interactive model iteration by generating labels using various signals such as heuristics, knowledge bases, labeling functions, and more to label data points rather than expensive hand labeling. And the way that we often do weak supervision is first we'll gather all these different sources that can generate labels, as mentioned here, and train some label model in order to actually get programmatic labels for all of the different data points. But then what we'll also want to do afterwards is train an N model to help with generalization, because weak supervision data sources may have low coverage on their own. And by low coverage, I mean that you may have a lot of data points in which let's say various labeling functions may abstain or not really vote, and we'll want to make sure that we're able to produce something that can generalize well. And of course, one problem with training large models is that they can be expensive to train, especially as we're seeing a trend these days in deep learning to just make a model with more and more parameters. So that can oftentimes be infeasible to people. One solution is to use transfer learning, which are, i.e., for example, deep networks, pre-trained on large data sets. For example, let's say that we're doing something with images, for example, we could pre-train on, let's say, ImageNet. It's a large academic data set with a bunch of images and labels. And, from that, we can sort of use pre-trained models to have a good sense of various features, and then sort of fine-tune that to whatever problem. But, fine-tuning in and of itself can also be expensive and can take work. But one sort of question we could ask is, we have these large pre-trained models that we could just run inference on and get sort of embeddings for. What if we can use sort of pre-trained embeddings to extend the coverage of weak supervision signals, rather than having to rely on, let's say, training some large expensive N model to use those embeddings. And that's essentially what Epoxy actually is. So yeah, the core idea behind Epoxy is to extend the coverage of labeling functions by having them vote on point where they would otherwise abstain by using the embeddings. And essentially what that means is suppose, let's say that I have two data points, one in which a given LF votes and one in which an LF does not. And I can use this, but let's say, for example, I can use the embeddings as let's say a notion of distance. For example, just switching gears here, let's say that these are documents, and I have a sort of doc-to-vec representation using using some sort of like model that's already been trained, and using that sort of doc-to-vec representation, I know that, you know, the points, yeah, the two data points are very similar. So I can say, okay, what if I actually use the way the LF voted when it did vote on the data point where it did not vote? And that way, you know, I can extend the coverage, if that makes sense. And, you know, we can sort of see that here in this diagram. So, you know, just to sort of walk through this whole diagram, here we have our unlabeled input on the left. We have various labeling functions here. So, you know, one that says, you know, if like, you know, checkout is in our document, we'll label it spam. And then, you know, if love is in our document, we'll label it not spam. And, you know, here you can see from this diagram that, you know, we have these like, you know, labeling functions just may have high accuracy, but sort of low coverage. And here we sort of have like, you know, these sort of pre-trained embeddings. You know, this represents some sort of like deep neural network that was like learned on some task. But, you know, the problem is obviously that these embeddings are not really discriminative for the task that we actually care about. These are just like, you know, general sort of embeddings. But, you know, what we can do is that then we can sort of combine them to create something wherein if we extend the labeling functions, we get something that's higher accuracy and higher coverage. So before I sort of like dive into how the algorithm actually works, does anyone have any sort of questions about, you know, what the problem we're trying to solve on a high level or anything like that? I'll just take a look at the chat. Okay, nothing actually in the chat. So any questions? Okay. Yeah, so generally also as a rule of thumb, I like to wait about 8 seconds after I ask that. So I'm guessing no questions for now. Let's move on. So before I like, you know, dive into the algorithm, I just want to point out there's a table in the paper. I believe it's on page 14 if you actually have the link, which just goes through a whole bunch of notation. So fair warning, I'm not going to be, you know, explaining or even using all of these things because a lot of it's relevant to various theoretical underpinnings that the paper does, perhaps to try and prove various results about how things work. But, you know, I'm going to be more focused on the basics of the algorithm and sort of how and why it works and how to actually use it. So I'm just going to be, you know, going through some basic notation here. So X, we have an unlabeled data vector, which is, you know, basically just a set of data points. Y is sort of like our ground truth labels, which we are saying are either -1 or 1. So for the purposes of this, we're going to be sort of like restricting ourselves to tasks of cardinality 2. The results can, you know, easily be extended beyond that, but the authors primarily like to do that because it's easier to, you know, prove various theoretical guarantees. Lambda I are various labeling functions, so they map from, you know, data points to labels. Yeah, other relevant notation. I'll explain some of these other ones later, but for now, I think we're good to proceed. And, you know, if you have any questions about notation, I'd recommend, you know, referring back to this if possible. I think it's a pretty useful guide. But anyway, so this is actually the core epoxy algorithm, you know, or as they call it here, labeling function extension method. So, you know, as inputs, it takes in a data set, you know, just consisting of a bunch of data points, you know, from I = 1 to n. It takes in some labeling functions, like, you know, this is a vector of labeling functions, big lambda, and it consists of, you know, m different labeling functions from lambda 1 all the way to lambda m. Some embedding distance function, dz. So, you know, to make this more concrete, if we go back to the example over here where I was saying, like, you know, doc-to-vec representations, cosine similarity would be our sort of distance function. We have threshold radii r, which I'll explain as we go through this algorithm, and a weighting function w, which I'll also explain. And basically what it'll return is these like lambda functions, like lambda 1 with a line over it, so lambda m with line over it. And essentially what that means is that's the sort of extended labeling function where we extend votes to otherwise abstaining points. So the way that this algorithm works is that we do a for loop over each labeling function in our vector and for each data point in our data set. And what we first use, if lambda j of xi is not equal to 0, then we set the extended value to be its actual value, or in other words, if the labeling function does not abstain, then we set the extended labeling function value to be what it originally was. And so also, in case it wasn't clear, the way that this paper uses its terminology is that if a labeling function abstains, it'll say lambda j of xi is 0. Just want to point that out. And then, let's say on the other hand, it does abstain. Then what we do is we basically compute the set of that data points labeled neighbors. And essentially what that means is, so using this formula here, so we're breaking it down. So the set of labeled neighbors here, and the way that we calculate that is, so we look at x contained in the support of lambda j, and the support of lambda j is essentially all data points in which the labeling function does not abstain. And we say, okay, we want to compute this thing. And what this essentially is that we want to look at the embedding distance between every data point where the labeling function does not abstain, as well as our original data point. And that's less than or equal to rj, where rj comes from this threshold radii here. So essentially what this is saying in sort of simpler terms, I suppose, is that we want to look at every data point where the labeling function actually labels something such that it's within some specified distance of our original data point. And the key idea behind this here, right, is that we want to make sure that the data points that we want to look at both obviously have a label, so we have some idea of how to extend it on the non-labeling data point, as well as that their embedding is sufficiently close, meaning that it's sufficiently similar. We want to make sure that we're not extending based on data points that are radically different. So the embedding distance gives us a notion of similarity. And so now we have some set of data points here, but then the question is, suppose, let's say, for example, they label things differently. How do we actually extend to the given data point in question? So if the set of neighbors that satisfy our criteria above is not equal to 0, if the length of that is not equal to 0, then we assign our extended labeling function vote based on some weighting function. And you can think of that again, that's something that we pass in here. So one example to make this concrete is, suppose, for example, that I want to pick the point with the closest embedding distance, right? Because the idea is the point with the closest embedding distance, even if we have multiple points that satisfy whatever criteria we set, that is the one that's going to be the most similar. So so you could also think of it if we're doing let's say nearest neighbors, that's the equivalent of a one nearest neighbor. So, and there could be other ways of doing it too. Maybe, for example, we want to find the most common. We aggregate all the data points that have a label, and we pick, okay, what's the most common label? That's another weighting function we could do. It's not one the authors mentioned in the paper, but again, it's just hopefully these examples give you a more concrete idea of what it is we're actually trying to do here. So, and then finally we have this other condition here, which says that if our given data point is not similar enough to any data points that the labeling function actually labeled, then it'll still abstain, because we don't really have any good signal on how to extend it, essentially. So this is the core algorithm and how it works. So here, just sort of going through some points I mentioned above, what sort of weighting rule should we use? In the paper, one nearest neighbor. And now another question, which may not be apparent is, what R should be used? So going back here, right, I mentioned before that we can like, set some sort of radius, for example, R, such that, the distance between a given like, pair of data points has to be at most this radius value. But how do we actually set it? It's not something that is necessarily readily apparent. And the authors basically note that the best performance comes from choosing a different R for each LF. And the authors note that setting R to be too large or too small can be suboptimal. Basically, if we extend our LFs too much, then we risk getting in bad signal, which will mess up the accuracy. And if we don't extend the LFs enough, then we don't get enough of the good signal to actually help us boost our accuracy. And basically, the best R values were found through doing a parameter sweeping, and I'll make that somewhat more clear when we get to the results section. But essentially, you can think of the process of finding which R values to use as doing like a sort of hyperparameter search when it comes much in the way that we might do for sort of like regular machine learning models. And so, what's needed for Epoxy to work? What sort of ingredients do we really care about here? And so, there are three things that we really want. One is that the LFs being extended need to be accurate. Two, the LFs being extended need to have reasonable initial coverage. And three, embeddings need to be smooth. And so, suppose that we want to extend an LF that's really inaccurate, then, well, that would lead to bad signal being propagated. And that would, again, mess up the point of Epoxy, much like if we decide to have an insufficient radius value, which leads to too much extension. It's a similar effect. The LFs being extended also need to have, sort of a reasonable coverage. Because, one sort of example of LF that people might write is people might write LFs that are really accurate, but really for very niche cases. Maybe let's say if you want to get some sort of corner case that's hard to label through more general labeling functions, you may want to have some sort of example like that. However, one problem with doing that is that, if those LFs are meant for very specific cases, then generalizing them would lead to them likely being inaccurate. So it's good to have LFs that not only are reasonably accurate, but also reasonably high initial coverage. So as an example, we'd much rather extend an LF that has like, let's say 80% accuracy with like 60 to 70% coverage than an LF that has like 99% accuracy with maybe like 1% or less coverage. And the third point is that the embeddings need to be smooth, and I'll explain what that means. So, the way that the authors in the paper essentially define smoothness is, what's the probability that given two data points that have the same label, they are considered similar by the embedding. So i.e. they have a distance less than or equal to some threshold. So smoothness is a function both of data points as well as whatever threshold we're choosing. So, because when I've been talking about embeddings and similarity, there's been the sort of implicit assumption that the similarity given by the embeddings is a good notion of similarity in general. But obviously, if that's not the case, and we find that if we find frequently that even if the embedding says they're similar and the labels are actually different, then that would again lead to a bad signal being extended. And here I want to sort of turn your attention to some graphs in the paper. And basically what the authors wanted to do is they wanted to sort of test out these sort of different hypotheses that I mentioned before of like, how does epoxy accuracy vary with LF accuracy as well as with smoothness of embedding. So the way that these graphs are basically calculated is that the authors made a toy problem in which they had three labeling functions. And they basically said, okay, I'm going to vary the accuracy of one of them. The other two are basically fixed with fixed class balance and an otherwise fixed problem. and they said that, okay, we're only going to extend one labeling function and keep the other two fixed. And so if we just extend one labeling function, how does the performance change as the accuracy of that labeling function varies, as well as like how the radius of our extension changes? And so if you look at this graph on the left here, we see that, okay, if the labeling function, here, like let's say in blue, right, it has an accuracy of 0.89, then we notice that, it starts out at a generalization error here of roughly 0.325. And, we see that as we vary R, it goes down a lot, hitting a sort of maxima or a sort of minimum generalization error here. And then it sort of like increases as we extend R. And you can notice that in all these different cases here. So there's sort of two things to note from this graph here. The first is that as the accuracy of our labeling function decreases, then we get sort of like, worse generalization error. So, this one with 0.89 is like the best. And then we see that as we decrease the accuracy, the generalization error gets worse. And, there's basically this sort of like sweet spot for what R should be. And, as we first, increase R, then we sort of get some of the benefits of being able to extend the labeling function more. But as we increase it too much, then it's being extended too much. And so now if we take a look at this sort of graph on the right here, they basically look at what happens when we sort of vary the smoothness. So what I mean by vary the smoothness here, so, this sort of comes from how the embedding labels were generated. So, they first took data points and generated them in a 10 by 10, 20 by 20, 15 by 15 in like random patterns. And essentially what that means is that you might like take a bunch of data points and say that, okay, 10 by 10 of them are some label, 20 by 20 are another, so on and so forth, in a sort of alternating fashion. And, what they found was that, this sort of pattern happens to lead to the embeddings being less smooth in this sort of way. And so, the 10 by 10 is the most smooth, 15 by 15, the next 20 by 20, and then, random is just, obviously just, worse. And here, so they took they had the same problem set up as on the left, and they took the labeling function that had the sort of 0.89 accuracy, and instead of varying the accuracy, they varied, the smoothness of the embeddings. And, what they found is that, the smoother the embeddings, the better the accuracy. So, here we can see, this plot here of the 10 by 10 matches up with this one here, because they use this 10 by 10 smoothness to generate these LF accuracies. And as you decrease the smoothness, the generalization error increases or accuracy decreases. Let's move on to some results. So basically, the way that these sort of results work is that the authors wanted to measure a couple different things. So they wanted to look at how epoxy does in the sort of setting that I described. And then what they wanted to do is they wanted to see, okay, what would happen if we sort of like, use the embeddings, but without fine tuning. So that's no fine tuning. So, transfer learning with no fine tuning, weak supervision with no fine tuning. And then here it's like, what if we just completely ditched the embeddings and just trained a sort of label model and used weak supervision on that? The authors happen to use a label model known as the triplets label model, which is mentioned in the paper. I'm not going to go into more detail on that just because it's not particularly relevant for analyzing these results. And here on the other side, they said, okay, what if we actually use like a fully trained label model, or sorry, a fully trained N model. So, in addition to sort of doing the weak supervision, they then trained an N model on top of that. And so basically the way that this table is sort of broken down is, we have different types of tasks. We have NLP tasks and video tasks. And then, by each task, you can see the embedding type. So basically, this comes from BERT, which is, a large language model. And they, use that to get embeddings. And then for the video tasks, they use different image models, like they use like, a large ResNet here, and they use like a bitransformer here. And so, and all these numbers are measured in F1 with the exception of the spam data set and the spouse data set, which are measured in accuracy. That was something that they did. And then here we can also see the sort of average training time, because, one thing that's important to know is that, obviously, again, with training an N model, right, it's more expensive to actually do in terms of time. So the authors also wanted to measure, not just how accurate what they were doing was, but also how much time it actually took. And so, here, for example, if we go through, the sort of, if we go through like the spam data set, for example, we see that Epoxy gets like, let's say an 89.6 accuracy. And then, if we take a look at the sort of, interactive speed baselines here, if we start with, for example, just like a label model with no actual data points, then, we can actually see that it gets some initial accuracy of like 83.6. If we do weak supervision with like, non-fine tuning, that does, somewhat better. And if we just take the embeddings with no fine tuning, that does the worst of them all. And so, one thing I should clarify is that if we do the embeddings with no fine tuning, what that means is that we take the embeddings from a large language model and train like, a simple convnet over them to get some values. Yeah, so to answer Ryan's question here, I didn't find any results in the paper that actually did like different results from BERT versus like, let's say, Sim CSE, for example. Perhaps once I go through these, I can take another look through the appendix and see just what the results were, but I didn't find any, just to my knowledge. And then if we take a look on this side of the table, we can see, how do things do if we add in an N model. And, one thing that I'll add is that, let's say, for example, we do weak supervision with fine tuning. For example, if we compare, let's say, this number to, Epoxy, it does turn out to be the case that the generalization benefits of adding in a fully trained N model versus do edge out Epoxy slightly in some cases, but, it comes at a cost of like a much greater training time. And, here we can actually see that if we do Epoxy and a fully trained N model, that's the best one of them all. So, it makes sense, right? Here, you're kind of combining the generalization benefits of both to get something that would generalize even more than one part on its own. But, sort of with Epoxy, you can like, come close to, or in some cases do better than the results of just a fully trained N model by itself, but for a fraction of the time. So that's sort of really what I want to highlight from these results. There are sort of a couple main takeaways here. The first being that sort of as we go through it, let's say add in a label model, then, add in fine tuning, and then Epoxy, we get a sort of, we get, speed ups on all of them. But then, if we do the embeddings by themselves without any weak supervision, then, that ends up performing, even worse. And then finally, with the sort of N models, we see a sort of progression there of, if we do like weak supervision with fine tuning and then Epoxy, we get better performance, but then Epoxy, even without an N model, approaches the performance of weak supervision with an N model. Oh, and then Ravi brought up a point which I'll read aloud here. So, I suspect that the model architectures themselves, what the embedding models are in pre-trained, would have a large impact. And Yeah, I definitely agree, because that goes back to the point of the smoothness of the embeddings, right? If the embeddings do a good job, then that would mean that we get good results. So I would not be surprised if the choice of embedding type does have an impact here, because of even just what we saw in the sort of synthetic section. And that's actually all that I have on the main paper itself. I hope this sort of gives as a sort of overview of how all these different steps come together, and how with just a little bit of augmentation, we can take the benefits of weak supervision and really push them through even more.
Hamza, that was a fantastic talk. Thanks so much for that, and we'll make sure to record it, edit this, and upload it to YouTube. So thank you so much